or we, as usual, we have like 19 minutes. Please go ahead, Moon.
皆様ありがとうございます。
Certainly, you improved your Japanese.
So the title of today's talk is Market Design with Deferred Acceptance, and I should tell that. So this is based on a joint work with Imamura-san and also Batadwan from University of Bristol in the United Kingdom. And this is our third lecture, and then today we will wrap up everything. So I want to first give some intuition of what we're doing. So market design has been exceptionally successful in bridging the gap between economic theory and real-life market. And our theory has been applied in many practical markets. For example, the deferred acceptance algorithm has been used in school choice, it's been used in college admissions, and then now there are many markets in which economic theorists and in particular market designers have designed the system. But how do we do this? Well, we need to persuade policymakers to implement the allocation rule that we think is good, right? So that we can have desirable outcomes. But how do we communicate with policymakers? So basically, when we communicate with policymakers, we need to talk about principles, right? And then principles can be thought of as axioms. For example, in the context of school choice, Alrov, Achilaftu Petrolu, Fatah, Tayfun Sönmez, they talk with policymakers and they talk about stability as a good principle or efficiency as a good principle. And then the deferred acceptance algorithm was implemented in New York City and Boston. So, in particular, when you look at the deferred acceptance algorithm, it is the unique, stable, and strategy-proof mechanism. This result goes back to a paper from 1990 by Odell Felder and Barbera. So, however, when you look at the deferred acceptance algorithm in general, the deferred acceptance algorithm needs an input, and those are the choice rules of school. Right? So, where do these choice rules come from? Right, so if you're designing the system from scratch, you need to specify the choice rules of schools, right? Or in other words, think about the setting in which there is only one school. The mechanism boils down to a choice rule. Students apply to this school, and the school needs to choose which students to admit and which need the students to reject. These institutional choice rules are sometimes very simple. There may be a given capacity and a single priority ranking over students, and the institution chooses students one by one according to the priority ranking until the capacity is full or you've chosen over the student. But sometimes they can be more complex because institutions may have distributional objectives, such as the ones that we've studied so far this week. And remember that, now, if you're also designing the choice rules, you cannot use the result that the deferred acceptance rule is stable and strategy-proof, the unique mechanism satisfying these two properties, because stability is defined using choice rules. So you get into this like circular kind of reason, right? So we need a different justification of the deferred acceptance rule when choice rules are also designed objects. Now, because we also need to think about which choice rules to use, we need to have a twofold justification. We need to have a justification for the priority design. Why should the institutions should use these choice rules? And then we take it one step further. Why should we use the deferred acceptance algorithm in which the institutions use these priority choice rules? As a result, we need a twofold justification. First, we need a justification of the institutional choice rule by an axiomatic characterization of axiom. And second, we need a characterization of the deferred acceptance rule based on these choice rules. Now, in this work, we thought about this a lot, and we came up with a method. The method is does the following. You start with a characterization of institutional choice rules of the schools, and from this, you get for free a characterization of the deferred acceptance rule in which institutions use these choice rules. So why is it important? Well, so from a practical perspective, this is useful, especially when institutional choice rules reflect complex objectives like distributional objectives and are difficult to justify. And conceptually, our work shed light on which properties of institutional choice rules are reflected in a market outcome when the deferred acceptance algorithm is in use. And especially, we established that the solitary choice axioms are always reflected in market outcome. So I haven't told you what solitary choice axioms are. We'll come to that in a second. But as long as the choice rule axioms are solitary, the properties of the choice rules will be reflected in matching outcome. And this will be a key property of our characterization. And then we're going to have one application of our main result, and it will be the case when feasibility constraints from a Matroid, and when we're using the greedy rule that we defined in the last lecture, right? So we already have a characterization of a choice rule we studied in the previous lecture, and it's the axiomatic characterization of the greedy rule. Now, after establishing our main result, we'll be able to get a corollary for free, which will be the characterization of the deferred acceptance algorithm in which institutions use greedy rule. If there are no questions about the motivation, I will go ahead and look at the model. So the model is similar to what we've studied so far. So it will be very similar to the previous lectures. Now, we have a two-sided market. On one side of the market, we have agents. So agents are denoted by, the set of agents is denoted by calligraphic A. On the other side of the market, we have institutions, and the set of institutions is denoted by calligraphic I. We are going to use contracts, so an institution and an agent can be matched under different terms, and that will be given in a contract, say X. So a contract specifies one agent, one institution, and the terms of the arrangement. For example, there could be a monetary payment between the agents. The set of contracts is denoted as calligraphic X. So sometimes we will be interested in the set of contracts signed by a particular agent or institution. So for a given agent A, the set of contracts that A has in step X is going to be denoted by XA. So likewise, given a set of contracts X and institution I, the set of contracts that I has in step X will be denoted by XI. So this is the standard notation that we've used so far in our lectures. Now, what are the preferences? We're going to assume that each agent and each institution has a ranking of the contracts that they are associated with. For agent A, there is a preference relation over the set of all contracts that agent A has and the outside option. Okay, so we denote it by this notation, so succeeds or is equal to. So this is a linear order. And we're going to say that a contract X is acceptable to agent A if the contract is strictly more preferred to the outside option. Likewise, for institution I, there is a linear order, or in other words, preference relation over the set of contracts that I has and the outside option.
So should I think of it as a case in which schools have actual preferences, or?
So it's a good question. So not necessarily preferences, but it could be preferences, or it could be like priorities that depend on exam score, right? Or it could be priorities depending on other criteria such as the distance to school and so on.
So let me just make sure. I understand. So I think you are talking about possibly the question of priority replacement design, but am I right that this part is not free?
That's right. So that's really important. So I should emphasize this. Even though we're going to actually design the choice rule or come up with axiomatic characterizations of choice rules that we are interested in, the preference relation or the priority order of institution I is given exogenously. Right? For example, like in the context of school choice, think about schools, and the schools determine their priorities based on some objective criteria, but in addition to that, they may have some distributional objectives, and the distributional objectives plus the priority will actually give us what choice rule that they should use. Now, what is an outcome? An outcome is going to be a matching. So this is a many-to-one matching. Therefore, we impose that each agent A can be assigned to at most one contract in a matching X, right? Where the institution can have multiple contracts. So we're going to be looking at matching rules. So a matching rule can be also called a mechanism. So we're going to fix everything other than the preferences of agents. So therefore, a matching rule is going to take a matching problem given by the preferences of agents and return a matching and if phi is the matching rule, and this is the preference profile of agents, then the outcome is going to be denoted by this phi of the preference profile of all agents. And then we're going to look at axioms on matchings, and they can be intuitively defined for matching rules as well. So a matching rule phi is going to satisfy a matching axiom if for each matching problem, the outcome produced by the matching rule satisfies the axiom. For example, what is the matching axiom that we're interested in? We're interested in individual rationality. So this is going to be for agents. A matching X satisfies individual rationality if for each agent A, the outcome for agent A is weakly preferred to the outside option. So a matching is individually rational when each agent either gets their outside option or gets an acceptable contract. So they shouldn't be assigned unacceptable contracts. And now we have this definition of individual rationality for matching. We can talk about a matching rule satisfying individual rationality. The matching rule will satisfy individual rationality if every matching that's produced will be individually rational. And finally, we're going to use the standard definition of strategic proofness. So we assume that institutions are not strategic, but only agents are. And therefore, a matching rule phi is going to be strategy proof if for each profile of preferences, no agent can misreport their preferences. For every misreport, the agent cannot get a more preferred outcome. Okay? So you guarantee to get the most preferred outcome by simply stating your true preferences, reporting your true preferences. So this is the standard definition of strategic proofness. Okay, so now we're going to introduce a new term. So we're going to classify choice axioms, so axioms on choice rules. And then we're going to say that they are either solitary axioms or not. Okay? So the second class we're not interested in, so we're just going to look at the solitary choice axiom. What is, first of all, okay, what is the choice rule? Now this is going to be design object, choice rule of institution I, and given any set of contracts that the institution can have, the choice rule is going to return a subset. So that's the definition of a choice rule. Okay, what does it mean to be solitary? A choice axiom is solitary if on each choice problem, it imposes a requirement that can be checked without referring to other choice problems. Think of it as this way. We have partial data on the choice rule, and we know the chosen set for this set of contracts. So we can check if there's a violation of this solitary choice axiom without knowing anything else about the choice rule. We don't need any other input. We just need the input on the sets separately. So now I will make this more formal. So let me just note that. So actually, Bumin defined this property, but he called it punctual. Right? So he uses the term punctual, but so we're going to call them solitary. Now I'm going to define it more formally. A solitary choice axiom is going to be a correspondence. It's going to take a set of contracts and it's going to return subsets that are allowed. Okay. So for each choice problem xi, the allowed subsets of contracts are given by phi I of xi. This is the correspondence. If this is the set of contract that's available to the institution, this correspondence will say which subsets are allowed. And solitary means that which sets are allowed for this budget set and another budget set are not related. So I will. So I want to make sure that this is clear, but I will give a couple of examples in a couple of slides. So solitary choice axioms. Okay, so let's look at our examples. Okay, so I guess first a couple of more definitions. Now, what does it mean that a choice rule Ci actually satisfies a solitary axiom phi I? It means that for every set of contracts, the chosen set is in this correspondence. So the choice rule is a selection from the correspondence. So therefore, for every set of inputs xi, the choice from the input must be in this correspondence. So phi I is a solitary choice axiom. And so phi I of xi will give us all allowed subsets that can be chosen by choice rules that satisfy this axiom. So therefore, for this input, the choice must be one of these allowed subsets.
Sorry, I'm being a little slow here. So again, so xi is for the choice. It's a choice problem, and choice problem simply means that subset of contract.
That's right. That's right.
Okay. So again,
Right.
yeah, thank you. Okay, I'm sorry. I'm trying to form a question. So this phi I. So here is phi I going to be depend on the institution's preferences. So namely, for example, I was thinking about some efficiency action, for example, but efficiency probably will refer to preferences of the institution.
You can think about like no justified envy, right? So we assume that the priorities of the institution is given, so it's fixed, it's exogenously given. So therefore, this solitary choice axiom can actually depend on the preference relation of the institution I.
I see, thank you. So this phi can potentially depend on preference of the institution.
That's right.
Thank you.
That's really important because we will give no justified envy as a solitary choice axiom.
Okay.
Any question?
Go back to the next slide. So what is capital C? Is the set of all choice rules for institution I.
Oh yes, sorry,
Oh,
yes, this is so. This is the class of choice rules.
Yes.
So, and we can just ignore it. So the choice rule Ci will satisfy the solitary choice axiom depend only this is true. And now we want to look at choice rules that are uniquely determined by a set of solitary axioms, or in other words, the choice rule is characterized by a set of punctual or solitary axioms. So what does it mean? A choice rule Ci is characterized by a set of solitary axioms, but this is a set of axioms, okay? And for every input xi, the choice from set I, from the set xi, is given by the intersection of these solitary axioms. So note that for each solitary axiom phi I, this identifies multiple sets that can be chosen. If the choice rule is characterized by this set of solitary axioms, when you take their intersection, you identify uniquely the set that has to be chosen. So we have correspondences, and the choice rule is a selection from these correspondences. But now we want this choice rule to be characterized by this set of solitary axioms. So that means if you take the intersection of the correspondences, you uniquely identify the set that must be chosen. Any questions on that? All right. So we already know a characterization of the greedy rule from the previous lecture. Let's just recall that. So now, to define the greedy rule, we start with a Matroid. For institution I, the ground set is going to be the set of all contracts, and then we have some feasible subsets of contracts such that this pair is a Matroid. Now we look at the greedy rule on this Matroid, and we said that the greedy rule is characterized by three axioms: feasibility, no justified envy, and the other one, what was the last one? Maximality. Okay. Now let's look at feasibility. Feasibility says that for every input, for every set of contracts xi, the chosen set must be feasible. Right? So really simple axiom. We want to show that this is actually a solitary choice axiom. So that's our claim. So this is a solitary choice axiom. What do we need? For this axiom, for feasibility, we need to construct a correspondence. It takes a set of contracts and it turns a collection of subsets of that set, such that Ci satisfies feasibility if and only if for every input xi, the choice must be in this correspondence. So the choice is a selection from the correspondence. Right? So this is what it means for feasibility to be a punctual axiom. So you can represent it as a correspondence like that, and this definition can be rewritten as follows. So for every input, we need to identify what sets are allowed, or what subsets are allowed. But in this case, it's really simple. So how do we define phi I of xi? So I think we have students in the audience, so I'm asking the students. So what is phi I of xi? Okay, so what does feasibility say? Well, feasibility says for every input xi, the outcome must be feasible, right? It must be in this set that is exogenously given. the claim is, okay, this axiom is solitary. So solitary axioms can be represented by choice correspondences. For every given set of contracts, this choice correspondence states what subsets can be chosen. So we need to define this correspondence for feasibility such that these two definitions are equivalent. So the choice rule I satisfies feasibility if and only for every set of contracts xi, what we choose is in the correspondence, is one of the sets identified by the correspondence. So what sets is the correspondence going to specify? Fi, right? Because we want the outcome to be feasible, and the set of feasible, so this is the set of feasible set of contracts. So this case is actually trivial. So for it doesn't depend on xi. Phi I of xi is going to be equal to this calligraphic Fi, right? For every input xi. Okay, so feasibility is solitary. Now maximality. So I wrote maximality this way. So what is maximality? So choice rule Ci satisfies maximality if for every input xi, if x is available but rejected from by the choice rule or not chosen by the choice rule, it must be that when you add contract X to the chosen set, what you get is not a feasible set. So it's not in this collection of feasible sets. Okay. So the reason that you're rejecting a contract X is because if you add it to the chosen set, you get a set that is not feasible. So again, our claim is that maximality is a solitary choice axiom. In other words, we need to construct a correspondence phi I, and for every input xi, the correspondence tells us which sets are allowed. So we need a collection of sets, subsets, and this definition will be equal to the following. So Ci satisfies feasibility if and only for every input xi, the choice from xi is a selection from the correspondence. Okay, so what do we need? So we need that so the choice can be feasible. Excuse me, so the choice can choose all the contracts. In that case, that's it. So the phi can be anything, right? Because if the choice is choosing all the contracts, there is no implication that this condition does not hold. So if we are choosing all the sets, then there is no implication, and you can just choose this randomly. So phi I of xi can be all feasible contracts. Right. However, if the choice is not equal to the set of contracts, so choice of xi is not equal to xi, so that means that actually there are rejected contracts, and this axiom will have a bite. So we need to be careful in defining this correspondence now. So what we need is, whenever we add a rejected contract, we get a set that is not feasible. How do we do that? Well, so we look at a rejected contract X, and then we look at infeasible sets that are not feasible. Right, so these are all, this is the collection of feasible sets. We look at the collection of all sets, and so this gives us the collection of sets that are not feasible. And here I'm abusing the notation a little bit. So if any set here has a contract X, I remove it. So I get a collection of sets here, so that when we add contract X, we get a set that is not feasible. all such sets? Well, whenever we add X, the choice union X is not feasible. So this tells me all sets that are allowed for the case of X. When I take the intersection for every rejected contract, I get all the allowed sets so that this property is satisfied. So our second claim that maximality is a solitary choice axiom is true because we can represent maximality by this correspondent. So that was our second axiom to characterize greedy rules. Now let's look at our last axiom. So our last axiom is no justified envy. No justified envy states the following. So choice rule Ci satisfies no justified envy if for every input xi and contracts x and x prime in the set xi, if contract x is chosen and contract x prime is rejected, then we have the following. Whenever the rejected contract has a higher priority than x, so there should be an I here. So whenever x prime has a higher priority than x according to I's preference relation, then removing x and adding x prime gives us a set that is not feasible. So we have a set of contracts. Now there's a rejected contract and an accepted contract. The rejected contract has a higher priority than the accepted contract. Then the question is, why did we choose a contract that has lower priority? The reason is if we remove the chosen contract and add the rejected contract, we get a set that is not feasible. Right, so this is no justified ending. So there is the rejected contract has a higher priority than the accepted contract. However, the school cannot swap contract X with contract X prime because that's infeasible. So that's why I guess the envy is not justified. Now, okay, so this is homework. We need to show that no justified envy is actually solitary or punctual. So the intuition is clear because when you look at this restriction, please go ahead.
The word punctual the same as solitary.
That's right, that's right. So William Thomson defined the property and he called it punctual. We used to call it punctual as well, but now we're changing it so that we're actually going to call it solitary. We have to apologize to William, of course, for changing the term. But what is the intuition? The intuition is that, so here, like when you look at the definition, you only see the choice from set xi, right? So let's see where we see the choice. Choice of xi, choice from xi, choice from xi. Nowhere in the problem we see anything else than choice from a different set. So that's why this is actually a solitary axiom. It doesn't depend on the choices from other sets. It just depends on the chosen set for this input. And we just check it separately. Okay, now we saw 3 solitary choice axioms. What about non-solitary choice axioms? Well, path independence. So we've looked at path independence in all lectures thus far, and we're going to look at it again because it's one of the most important choice axioms in market design. So it says that for every set of contracts xi and xi prime, the choice from the union is equal to the choice from the first set union the second set. And now my claim is that path independence is not a solitary axiom. Why? Well, the intuition is clear. In the definition, we are looking at choices from 3 different sets. Choice from xi, choice from this set and the choice from the union. So it is not solitary, it is relational. It relates the input from different choices. Okay. Now the second most important choice axiom is the law of aggregate demand. Go ahead, please.
So, I guess it is indeed very intuitive that path independence is not solitary, but it is possible that somehow actually it is solitary but happens to be represented as if it is not. So
that's right.
It is easy to see that indeed it is. There's no way to write it as a.
So it actually needs a proof. The proof is using this idea that, so if you have two choice axioms, excuse me, if you have, okay, so one way to prove that an axiom is not path independent is as follows. If a choice rule is actually solitary or punctual, now the following property holds. Take a choice rule that satisfies the property, the axiom, and take another choice rule that satisfies the axiom. Now, you mix the two choice rules as follows. For every input xi, now you define a new choice rule, and a third choice rule, and the third choice rule outputs either whatever the first choice rule outputs or the second choice rule outputs. This new mixture has to satisfy the choice rule axiom as well.
That's the implication of solitariness, but you are saying that. Okay.
So maybe I should write it. So this is a proposition. So Ti double prime is a mixture of Ti and Ci prime if for every input xi, Ci double prime xi is equal to di xi or di double prime xi is equal to di prime xi. And now the proposition says that so an axiom is solitary if and only if every mixture of choice rules satisfying the axiom is also satisfies the axiom. So one way is actually easy to see, right? So take a solitary choice axiom and take two choice rules, Ci and Ci prime, that satisfy the axiom. So what does it mean? For every input xi, choice of y xi is allowed, right? Defined by the correspondence, and choice I prime xi is also allowed, given by the axiom, the correspondence for the axiom. If you do a mixture, then choice I double prime of xi needs to be one of those two allowed sets. Because it's one of those two allowed sets, then choice I double prime also satisfies the punctual choice axiom. So one direction of this is trivial. We also show that the other direction is also satisfied. To prove that path independence is not a solitary axiom, so we look at two choice, I think we just need a couple of contracts. And then we look at two path independent choice rules and we provide a mixture, and the mixture does not satisfy path independence, even though the two choice rules satisfy path independence. And the second most important in market design, the second most important choice axiom in market design is the law of aggregate demand. It says the following: if we have two, okay, so I'm missing something here. So if we have two inputs, xi prime and xi prime is a superset of xi implies this. Okay? And again, the law of aggregate demand is not solitary. We prove this using this proposition. However, you can see the intuition that the axiom is satisfied by comparing the cardinality from two different chosen sets. So it is relational, not solitary. Any other questions? Now what we're going to do is an operation. We're going to start with a choice axiom that is solitary, and we're going to extend it to matching rules. So we're going to get an axiom on matching rules. Okay? So the method works as follows. Again, we're fixing an institution I. We are fixing a matching problem. So we're fixing the preference of all agents and a matching X. Now we're going to define this concept called the demand for institution I. How do we define the demand for institution I? Well, before that, let's introduce the following notation. The agent associated with contract X is denoted by alpha X. How do we determine the demand for institution I? Well, every agent looks at the following. Do I have any contract with institution I that I weakly prefer to the contract that I have at the moment? Right? So right now I have this contract with some institution. Now we are determining the demand with another institution. Would I rather have any other contract with the first institution? If the answer is yes, then these contracts will be included in the demand. So we look at the demands of each individual agent, and then we take the union of that to get the demand of institution I. So, more formally, the demand for I at X is the set of I's contracts that are weakly preferred by the agent associated with the contract to their assignment. So we are looking at the demand of institution I given a matching X. We are including all contracts X such that X is weakly preferred by the agent associated with this contract to whatever they have in matching X. So we are including the contracts that the institution already has in the demand set because this is the weakly preferred relation. The extension of solitary choice axiom phi I to matchings is denoted by phi I upper bar and is defined as follows. So a matching X satisfies the extension of phi I at the matching problem if xi is allowed by the choice correspondence when we look at the demand set. So we are doing two things. First, at the matching, we are calculating the demand for institution I. Right? So these are the set of contracts that the institution could have if they wanted, because all the agents want to switch to institution I using those contracts. Now, the choice axiom for this particular problem tells us which sets are allowed. Now, the matching is going to satisfy the extension if the set of contracts that the institution has is in this correspondence. So whatever the institution has at the moment is one of the allowed sets from the demand set. So maybe an example will help, but let's look at the example. Now, we had feasibility for the choice axiom. So what does feasibility say? The sets that we are choosing must be feasible. The extension will say the same thing. For each institution, the set of contracts that the institution has must be feasible. Okay. So this is the extension of feasibility to matching rules. Now, what about maximality? So maximality for the choice axiom says that if a contract is rejected, adding it will give us a set that is not feasible. Now, the contract that we're going to add has to be demanded by the agent associated with the contract. So we add this condition that. So for each institution I, if X is a contract that I can sign, but it is not in the matching XI, and X is actually preferred by the agent associated with it to the contract they have in matching X, then it must be the case that adding X to Xi will give us a set that is not feasible. Now, the only difference with the choice rule satisfying maximality is that in the choice rule property, we could add any set that was available to the institution but not chosen. Here, a contract is available to the institution if and only if it's in the demand set. Being in the demand set and not being in matching means that the agent associated with the contract strictly prefers the contract X to whatever they have in matching X, and therefore maximality for matchings will mean that adding that contract will give us a set that is not feasible. So of course, I'm claiming that feasibility of choice rules has this extension, and maximality of choice rules has this extension, but these need to be proved formally. I'm just giving you the intuition right now. Now, for the last one, I'm going to cheat a little bit. Instead of showing you no justified envy the way we defined it so far, I'm going to look at a different definition of no justified envy that we can use. The reason I'm doing that is it allows me to introduce the rank function of a Matroid that we haven't used so far in the lectures, but I want to talk about the rank function as well. What is a rank function? So, the rank of any set of contracts Xi will be denoted by Ri of Xi, as it is defined as the cardinality of any maximal independent subset of Xi. So we look at this set of contracts Xi, we identify all subsets of Xi that are independent. Right? So independence is given by the Matroid.
Right, so let me so Xi doesn't have to be in the Matroid, but you already fix the Matroid and then independently refer to this Matroid.
That's right. So Xi doesn't have to be an independent set, right? But what we do is we look at all subsets of Xi and we identify those subsets that are independent, so that they are in the Matroid. And then the rank of Xi is defined as the maximum cardinality of independent subsets. And this is well defined, of course, because all maximal independent subsets have the same cardinality in a given Matroid. So it turns out that the rank function of a Matroid satisfies three properties. And furthermore, if you start with a rank function satisfying these properties, then you can construct a Matroid such that this function is the rank function of the Matroid that you constructed. Okay? So what are the three properties? The first property is that for any given set Xi, the rank of Xi has to be between 0 and the number of contracts in set Xi. Of course, this is obvious, right? Because this is defined as the maximal the cardinality of the maximal independent subset. So therefore, it has to be between 0 and the number of contracts in Xi. The second one is the monotonicity condition. If xi is a subset of xi prime, then the rank of xi is less than or equal to rank of xi prime. Again, this is obvious from the definition. Why? Because the maximal independent subset of xi is also an independent subset of xi prime, and it doesn't have to be maximum. Therefore, the rank of xi prime is going to be greater than or equal to rank of xi. And finally, the property that is perhaps not trivial is the so-called submodularity property. For every set of contracts xi and xi prime, the rank of the union plus the rank of the intersection is less than or equal to the sum of the two ranks. So this is the submodularity property of a function that you may have seen before. What is the interpretation for the rank function? So if the rank is, so sometimes rank function can be used to measure how well distributional objectives are satisfied. For example, let's say that we are reserving some number of seats for minority groups, then the rank function will give us how many reserved seats we can fill. Okay? So for some of the Matroids that you will see in market design, the rank function will be a measure of how well distributional objectives are actually satisfied. Now, using the rank function, I can rewrite the no justified NV axiom for choice rules, and I can extend it. So I will just give you the extension. So a matching X satisfies no justified NV if for each individual I and a contract that for each institution I, and a contract that the institution can have, and a contract Y that the institution can sign but not in the matching, if the agent associated with the contract Y prefers Y to whatever they have in matching X, the following holds. So if Y has a higher priority than X for institution I, then it must be that if we swap contract X with contract Y, the rank actually goes down compared to the original set. So here again, we have an agent, alpha Y, and they want to sign contract Y with the institution. The institution, on the other hand, has a contract X in the matching. And it turns out that the rejected contract has a higher priority than the accepted contract. What is the implication? The implication is that if we swap contract Y with contract X, the rank is going to go down. So if you use the interpretation of the rank function, the distributional objectives are going to be satisfied less. That's why we are choosing X instead of Y. So this is the
So I see. I think in the choice case, I'm trying to remember the definition in the choice case. In this choice case, you actually, if I remember correctly, yes. So swapping actually resulted in infeasibility, and here you are not mentioning the requirement of feasibility, and I'm still trying to understand why this is.
Sure. So we could actually rewrite this condition using feasibility axiom. So what are we imposing on feasibility? The choice must be feasible, right?
Right.
So choice being feasible means that we are choosing an independent set of the Matroid, and for independent sets, the rank is equal to the cardinality of the set.
Right. Right.
So whenever we do this swap, we no longer get a feasible set. And for sets that are not feasible, for sets that are not independent, the rank function is strictly smaller than the cardinality of the set. So a set is independent if and only if the rank of the set is equal to the cardinality of the set. So this is a property of Matroids. So therefore, this condition can be written as the rank of this set is strictly smaller than the rank of the chosen set.
Thank you. So given that, let me make that understand. So given that C function is already assumed to be always return the feasible outcome, which is in f of I, this condition of not just ND for the choice function can be written in the exactly sort of same way as what you did for the matching. That's what you're saying? Okay, I see. And then that also suggests that in your definition of matching, I guess you did not impose a feasibility, and hence the same way cannot be written. I mean, this version cannot be rewritten to be the version which is the same as the choice function case, as I understand. But
So I think it can be written, but it will be easier to write. Will be also like you're just asking if the axiom can be written just using without using the rank function.
yeah, if you don't use the rank function, then
So I think so. This will be not feasible.
is that the sorry. So when you take this matching, is it already assumed to be feasible? So I thought that you were saying you are not.
So we're imposing all the axioms together. So and then like the same characterization result will hold, even though the axioms by themselves may not be exactly the same.
Yes. So let me make sure I understand. So I guess you will somewhere impose the matching to be feasible. That's important.
That's why yes, that's why.
Here, are you already assuming that the matching is feasible? Then when you introduce this definition.
So here I'm not assuming that.
Okay, that's right. That answers my question.
That's it. But what is important is, like, we can likely change the way we write this axiom. So even though the axioms are not exactly the same, we will get the same characterization result.
Okay.
So like under feasibility, these two axioms will give us the same thing. So feasibility plus the first version will be equal to feasibility plus the second version. So, but the only reason why I defined it this way was to actually introduce the rank function, because so we covered the axioms for independent sets in the second lecture. We also covered the axioms for bases of a Matroid in the second lecture. I also wanted to talk about the rank axioms or rank properties, so that's why I introduced the axiom this way. Now the results. So the results are, of course, going to use the deferred acceptance algorithm, because from a characterization of choice rules, we want to go to a characterization of the deferred acceptance rule in which these particular choice rules are used. So let's just remember the definition of Gale-Shepard deferred acceptance algorithm. Each agent proposes their most preferred acceptable contract if such a contract exists. Each institution I considers all the proposals, say, given by this set X1C, and tentatively accepts the contracts in the chosen set and permanently rejects everything else. At any given step, each agent whose contract was rejected in the previous step proposes their next most preferred acceptable contract, if such a contract exists, otherwise they don't make any proposals. Each institution now considers all the contracts they have tentatively accepted from the previous step and all the new proposals coming in at this step. They apply their choice rule, tentatively accepts the chosen set of contracts, and permanently rejects the rest. And we continue until there are no rejections or there are no more proposals. The DA based on the deferred acceptance rule based on this choice rule profile C produces at each problem the matching defined by the acceptance at the last step of the deferred acceptance algorithm based on C. So this is just the way to define the deferred acceptance rule based on C. So our main result is as follows. Now suppose that for each institution I, the choice rule Ci satisfies path independence and the law of aggregate demand. Furthermore, This choice rule is characterized by a set of solitary axioms given by phi I. Then a matching rule satisfies individual rationality, strategy proofness, and the extensions of these solitary axioms, if and only if it is the deferred acceptance rule based on choice rule profile C. We are starting with the characterization of institutional choice rules. And furthermore, we know that path independence and the law of aggregate demand are also satisfied. Then using this result, we can get a characterization of the deferred acceptance rule based on C by extending the solitary choice axioms and adding to that list individual rationality and strategy proofs. So why is this actually helpful? Well, in the literature, there are papers studying different choice rules. For example, there's a characterization of responsive choice rules. There's a characterization of choice rule reserves. These choice rules are characterized by solitary axioms, and furthermore, they satisfy path independence and the law of aggregate demand. Now, apply this result. You will get new results as corollaries. You will get a characterization of the deferred acceptance rule in which institutions use responsive choice rules. And you will get a characterization of the deferred acceptance rule in which institutions use responsive choice rule with reserves.
So in your paper, so I'm trying to remember. So in your paper on like results, your first paper, my recollection is that indeed you kind of like had properties related to this result on the sort of matching, and then actually you kind of show that corresponds to the choice, to certain choice rules with different acceptance, if I remember correctly. I wonder if those assumptions can be actually mapped to as a sort of some similar thing.
Thank you. So you're referring to the paper with Federico, like the
sorry. Actually, what I actually meant is that your paper is Isa and Mohammed.
I see. So there,
I'm
define. Yeah, so we define deferred acceptance algorithm with reserves in a case. So, but we don't provide an axiomatic characterization of this rule. But as you said, we can get a characterization of deferred acceptance with reserves just by taking the characterization, say, from Echenike and Yenmez choice rules with reserves and applying this extension. But there's one small point that I think in Echenike and Yenmez we used substitutability or path independence to do the characterization. Now we can't use that. So we have to substitute it with another axiom, but maybe Imamura-san's paper has a characterization of choice rule with reserves and quotas using solitary choice axiom.
Without substitute.
Oh, with substitute, okay.
Without.
As I said. But it's easy to come up with a different characterization, so maybe that's a homework. Come up with a characterization of the deferred acceptance algorithm with choice rules that are all solitary, and just apply this result to get a new result that is not in the literature. We're going to do just that. So we've seen the characterization of greedy rules, and we provided a characterization using just solitary axioms. And we know that the greedy rule satisfies path independence and the law of aggregate demand from our second lecture. Therefore, we can apply the previous theorem, and we get the following corollary. A matching rule satisfies feasibility, rank maximality, so maximality, nor justified entity. So these are the extensions of the solitary axioms to the matching rules. And to that list, we're adding individual rationality and strategy proofness. So a matching rule satisfies these 5 axioms if and only if it is the DA deferred acceptance based rule on the greedy rules. So you can repeat the same exercise for any characterization of choice rules using solitary choice axiom. Any questions before we can conclude?
So, can you explain again how to interpret this extension part? So, I think you gave several examples, and in these specific actions, I felt that they made a lot of sense. I mean, indeed, they seem to correspond to the sort of existing actions overmatching them. Hence, it seems like a very natural way to do it. But then, I still am not clear enough to understand why this is the sort of quote unquote right way to extend this action into the matching exercise. So maybe I admit it's a very vague question.
No, it's an important question. I mean, the way we define it is mathematical, although in the paper we give more intuition about it. So let's look at the extension. So let's go back. Okay, so xi has to be in phi I dix. So phi I identifies subsets that are allowed. Now you can view this institution. Now in a matching problem, you can view the institution as having a particular choice problem, right? So now I have the set of contracts that I already have, but in addition, some other agents want to sign contracts with me. So the institution is facing a choice problem, and the choice problem is given by the demand, right? I have all the contracts from the matching already, and there are other agents who want to switch and who want to match with me. Now, so it is as if I'm facing a choice problem given by the matching and the preferences of agents, so that I need to make a choice from the demand set. So the demand set is giving me all contracts that I could possibly have. Now the axiom, the extension to matching is going to be satisfied if the set of contracts that I already have is one of the allowed sets identified by the correspondence, right? Because phi I gives me which sets of contracts are allowed. Now I'm facing a choice problem given by the demand. And the axiom is, the extension is satisfied if the set of contracts that I have is one of the allowed sets. So, I mean, I guess, kind of explained what the definition is again. So I don't know if it gave any intuition, but try any punctual axiom and extend them. They will always, you'll see that they will always give you the right notion.
Can you show the slide for the statement again?
The main result.
Yeah, main result. That's really important. So, make sure I understand this. So you're saying that the choice rule CI such is already assumed to be independent and by the demand. When you say it is characterized by a set of solitary actions, does that mean that is it okay to characterize CI with these solitary actions plus independence and overall demand, or?
It's a good question. So in that case, one result will hold. Of course, like if the choice rule is characterized by path independence for the demand and solitary axioms, then the A rule with these extensions will satisfy individual rationality, strategy, proofness, and the extensions, but the one direction will not hold.
Sorry, I couldn't follow you. So if we, so as written, what you mean is that actually the choice function itself is characterized only by a solitary action rather than these actions that has independent and I see. And then if another version, which is that the choice actions are characterized, choice functions are characterized by both of these two, then
you get independent LAD and the set of solitary axioms.
then direction.
So then this direction will
Only if mean if or if but.
yes. So
yes, okay, I see.
so then the rule based on these choice rules will satisfy individual rationalities, such improvements, and the extensions.
I see.
However,
so that seems to be true. Okay, good.
However, a matching rule that satisfies individual rationalities, such improvements, and the extensions doesn't have to be the deferred acceptance rule based on that profile.
Oh, that's okay. Oh, I see. Okay.
So that's an important point. Thank you for bringing it up.
Thank you. Maybe this is a related question, but then I guess what you seem to be saying is that if instead of item 2 in hypothesis, yeah, so instead of this CI is being characterized by the set of actions, if we just require that the choice function satisfies the some solitary action, then I guess DA based on this choice function, satisfies this basically situation.
So it's easy. We can strengthen one part of the result, so we don't need the characterization for the matching rule to satisfy individual rationality, strategy improvements, and the extensions of the solitary choice axioms. As long as the choice rules satisfy the solitary axioms and path independent LAD, this result will hold. One direction will
The other direction is not.
In particular, that's why I think, so maybe we should emphasize it that if the choice rule satisfies a solitary axiom, then the deferred acceptance rule based on C will satisfy the extension. So if there are no further questions, we can conclude. So remember that the greedy rule gives us optimal solutions over Matroids. Now we have a characterization of the greedy rule from the first lecture, and now using this new method, we get a characterization of the deferred acceptance rule in which institutions actually use the greedy rule. But our result is much more general than that. For any characterization of choice axioms based on solitary axioms, as long as these choice rules satisfy path independence and LAD, we also get a deferred acceptance rule characterization based on these choice rules. Well, so the takeaway is considering the choice rules studied in the market design literature. If there is a characterization by solitary choice axioms, then you can apply our results to get a characterization of the greedy rule. If there is no characterization by solitary choice axioms, then it's an opportunity. Provide a characterization using solitary choice axioms, and then apply our result to get the greedy rule characterization, and you get a new paper. So this is our third and last lecture, and thank you all for minna arigatou gozaimasu for attending all the lectures, and thank you for your hospitality. And please, if in the future you have any questions or you want to contact me for some reason, please feel free to send me an email.
So he just invited questions. So if you have any questions, it's a great chance to ask him. I think you are leaving like tomorrow. Is that
Sunday?
Sunday, right? But I guess tomorrow is the weekend. So before he goes, I think
I
characterization. So in the beginning, introduction part of this talk, you mentioned that this kind of characterization approach is important when we talk to policy makers.
Yes,
Right. So how directly are you kind of using this characterization result when you talk to policy makers?
So I haven't used it so far, and I don't know if anybody has used it, but I think like this is the, I think like when like talking to policymakers, of course we cannot talk to them about the mechanisms and their properties and so on. So, however, if we have a characterization using axioms, then we can try to identify each axiom with a principle. And then we can talk to them about the principles that we would like. For example, individual rationality. You cannot assign a contract to a student that the student finds unacceptable. So as long as you have a characterization of a mechanism or a matching rule based on principles, I think it will be easy to convince policymakers. However, so this statement is a conjecture at this point. So hopefully it will be proven in the near future.
So I think my question will be much less interesting, but so you have this characterization result. So it characterizes the sort of the choice rules are characterized by your solitary axioms, and so then you get this characterization of DA in terms of the extension of the algorithm plus IR and suggestiveness. So do you know whether these axioms created in this way? I mean, in this conclusion part of your conclusion statement, then is there any way that you can show they are independent axioms?
Oh, I see.
When there's a choice rule characterization.
So the question is as follows. So whenever we provide a characterization, we want the axioms to be independent. So basically, like remove any axiom. Do the remaining axioms imply the one that you removed? If that's not the case, then we say, okay, these axioms are independent. So now, ideally, you want to start using our result by a characterization with independent axioms. So Kojima Sensei's question is like, let's extend them to matching rules. If we know independence of the choice axioms, do we automatically get independence of the matching rules? My intuition will say yes, because the choice rule is actually a matching rule in which we have only one institution. So if they were if the axioms were not independent, then there are more institutions. They will still be not independent when there is only one institution. So I think, but we need to formalize this intuition. But I think the answer to your question is yes.
I think, thank you. That's very sounds true to me.
But we need to check. Any other questions?
Like everybody is very happy. So let's great. So thank you very much. So let's thank Professor Bumin Yenmez again.